So it's February 7th, and we're just going to be continuing with the lecture from last time, which is mostly focusing on noise, of course. But before we do that, just logistically, homework number 2 has been posted. So make sure you go and take a look at that. Make sure you start early. You should already actually know how to do a reasonable sort of chunk of it. But certainly by the end of the day, you should have pretty much everything that you need to do that completely. So any sort of questions either on material so far or homework or logistics or anything like that? Okay, great. So if not, let's go ahead and dive back into our sort of course of the material. So last time we started talking about essentially noise and where it comes from in circuits. And in particular, we just finally started getting into talking a little bit about how you'd actually calculate or really think about how to get the total noise in some given particular circuit. So we talked a bit last time about how there was this so-called fluctuation dissipation theorem that basically said that the only way you could actually have an element generate thermal noise was if it could actually dissipate power as well. And we kind of went through the example of that with the resistor and the capacitor. But so the question is that when we then actually have a circuit that actually has, let's say, a resistor and a capacitor in it, if we really are interested in figuring out what the noise characteristics of that circuit are, that's not to say that even though the capacitor doesn't generate noise, and actually let me draw it slightly differently, that even though the capacitor doesn't generate noise, that it has no effect on the noise. Okay? And by the way, this is true not just of capacitors, but any, let's say, generic energy stored element. So capacitors, inductors, transformers, and etc. So let's just think about a simple example where we have a resistor and a capacitor. Okay? And I've drawn it kind of this way because I'm going to obviously add in my noise source, my noise voltage source to model the noise of the resistor. But really, this is actually just sort of a model of a resistor and a capacitor in parallel with each other. Okay? Because you can imagine if I sort of drew the ground closed like this, you get rid of the noise voltage source, and I'm looking at the output like this, then the resistor and capacitor indeed are just essentially in parallel with each other. Okay? So the general way that we're going to actually think about how to figure out the total noise in some given circuit, and by the way, in this case, I'm not just saying let's say, from one particular source, but it could be from all of the sources. And also, it's not just, let's say, the total noise, but it's even the noise as a function of frequency. Then what you really have to do is essentially figure out how that noise is essentially filtered by all the passive elements. Okay? So let's just take this particular example to sort of show what I mean by that. So here, this is, of course, our noise source, right? And so what we want to know is how does that capacitor actually affect the final noise that you'd measure at the output, where that output is just defined as the voltage across the capacitor itself. So in general, the sort of method that you should use is essentially you have to figure out what is the transfer function from the noise source itself to the actual output that you're measuring. Okay? So I'm just going to redraw this one more time just to make sure that everything is sort of absolutely clear. Right? So in other words, our noise voltage source is really being applied here, right? And we're going to measure the output there. Okay? So ignoring the fact that this is a noise problem, if I just asked you for the transfer function of this circuit, what would that transfer function be? In other words, what would V out of S over V in of S be? Yeah, exactly. Just 1 over 1 plus S RC. Okay? So the way this is actually going to affect us from a sort of noise density standpoint is now if we do a plot versus frequency of essentially the log of the output noise density, then now what we're going to see is that if originally that resistor had so-called white noise, which as a reminder means that it would have looked flat versus frequency, then if we just do, then I'll just do this in a slightly different color. Once we actually have this capacitor here, instead, what you'll get will be something that obviously looks like a low-pass filter, something like this, right? So the whole sort of trick with calculating noise in general in circuits is actually, at least conceptually, very straightforward. All you do is you figure out this transfer function for each and every single sort of noise source in your circuit. And by the transfer function, I just mean the ratio of whatever your output quantity is, let's say the voltage, to whatever the input noise source is. Figure that out as a function of frequency. And then basically you figure that out for each individual noise source, and you add them all up together. Okay? So that's kind of all this equation up here is saying. It's basically saying you take that transfer function, you multiply it by the noise source, and then you add all of the different sources together. Now, one more thing that I should point out here just to make sure it's absolutely clear. Notice we're always dealing with variances, right? So when you add the noise sources together, you have to add them in variance. That's the first important point. The second, equally important, if not even more important point, is that notice I'm not just multiplying by the transfer function itself. I'm multiplying by the magnitude squared of the transfer function. Because if you kind of think about it, I could always model this noise source as being kind of like a bunch of smaller narrow band noise sources, right? All kind of concentrated around some particular carrier frequency. And then I would say that at the end of the day, the sort of total noise was just adding up the contribution from each of those frequency components, right? Well, if I'm doing things that way, then indeed each of these sort of little narrow band noise sources is independent of the other ones. And so when you add them together, you better be adding in variances, right? Now, by the way, this also actually tells you if you were interested not just in the noise density or the spectral characteristics of the noise, but you actually wanted to know at the end of the day how many millivolts of sigma variation do I really have. This actually tells you exactly the way you do it. Because what you'd basically do is you'd take that transfer function, and all you do is you just integrate it across all of these different frequencies to find out the total, essentially, area under the curve. That's exactly what would tell you the net noise variance in this particular case. Does this make sense to everybody? Or? Okay, so if that's clear, just keep that in mind, by the way, because we're going to be using that again in 1 second. Well, maybe not in 1 second, but maybe halfway through this lecture to really do some very specific circuit examples. But before we do that, I do need to talk a little bit about some of the other elements in our circuits that will generate noise. So we talked a lot about resistors already. We said also that things like capacitors, inductors, transformers don't generate any noise, but they only filter it. In other words, they'll modify that H of S that we just talked about. But of course, we're going to have lots of other elements in our circuits that indeed can dissipate power, and therefore could also actually generate noise. And so just to start with, let's think about, for example, a diode. Okay? So diodes actually, in particular, are somewhat interesting here because they have a slightly different type of noise. And that type of noise is so-called shot noise. Okay? So before I sort of dive too much into the details of kind of what shot noise is, let me sort of tell you a little bit what the final result is, and then maybe ask you guys if we can guess why it is that, or where this particular type of noise is coming from in the first place. Okay? So if we take a diode and we look at its so-called shot noise, the noise current density will just be equal to 2 times the electronic charge, Q, times the drain current, the DC current that's actually flowing through, the instantaneous current flowing through that diode, times the bandwidth. Okay? Now notice this is very different than thermal noise was, because we said that in thermal noise, the drain current density didn't matter at all, right? Like the thermal noise was totally independent of what you kind of did, for example, to the resistor. Here it's directly proportional to how much current you have in the first place. And actually, interestingly enough, it's also related to the electronic charge. So, anybody have an idea of where shot noise is actually coming from? Why, how the heck did the electron charge kind of come into the picture here? By the way, who's actually heard of shot noise before? Oh, okay. So in that case, you guys should all know the answer. So what's shot noise actually associated with? Okay, so you said charges arrive at a random time in the space charge region. That's actually correct, but in exactly the, and I'll come back to you in 1 second, in exactly the way you described it, that wouldn't necessarily be excluded from this happening in a resistor as well, right? A plain standard resistor could have potentially also had this. So what's really different about shot noise? DJ? Okay. So you said it's randomness of charge jumping over a barrier. So the key difference between shot noise and thermal noise is that in shot noise, there's a barrier that basically blocks current or blocks electrons from moving in one direction versus the other. Okay? So the real big difference here is that with shot noise, there's that barrier that's basically sort of, at least conceptually speaking, allowing things to flow only in that one direction. Okay? Whereas in a resistor, there's no preferential direction for current, right? Either which way is the same. Okay? So as we'll see in 1 second, there's actually sort of an interesting argument as to why shot noise and thermal noise in many ways are fundamentally sort of coming from the same thing. It's just that in one case there's a barrier and the other one there's not. Okay? So I've given you obviously some example numbers here, but instead of sort of spending too much time on that, let's really take this example and see why it is that shot noise and thermal noise might really actually be related to each other. Yes? Oh, this is proportional to bandwidth the same way that thermal noise is, in the sense that this is really just a white noise source, at least white up to any frequency that we as electrical engineers doing, let's say electronic circuits are probably going to care about, unless people get, really ridiculously new, weird technologies that let us get out into multiple hundreds of terahertz. Okay? But it's just proportional to frequency in the same way that the thermal noise is. So really, to maybe list this more precisely, it's just saying the noise density is 2q ID. Okay? And of course, depending upon what your real circuit bandwidth is, that would change the net integration that you would get across frequency. By the way, just as I also mentioned here, it's independent of temperature. It's actually zero mean and Gaussian. As I said, it's also white. But all of that should not be very surprising. Pretty much all of the noise sources we're looking at will basically have those characteristics. Okay. So again, let's sort of do a simple thought experiment to see why shot noise and thermal noise might actually be related, even though one of them is independent of temperature and the other one clearly is directly related to temperature. Okay? So let's just imagine we took a diode, okay? But I didn't actually know that I had a diode. In other words, I take that diode and I kind of put it into a black box, okay? So that basically all I can do is I can take that diode and I can apply a voltage to it. And let me actually switch colors so maybe it's a little bit easier to see. So I'll just draw this again so it's a little bit easier. Okay, so I take that diode, again, I put it into a black box, and I can basically apply a voltage and measure how much current is flowing through it. Okay? So if I do this experiment, just like sort of all of the analog designs that we do, at some given particular bias point, I could always measure what the sort of effective conductance, small signal-wise, of that diode was, right? And just like we said with bipolar junction transistors, because it's an exponential relationship between current and voltage, when you take the derivative, in other words, you find that small signal relationship, you'll again just get something that's proportional to the drain current in the first place, divided by kT over Q, right? Okay, so if I've done that, what I could then next say is, well, okay, if I have that small signal resistance there, let me figure out what the sort of effective thermal noise from that small signal resistance would have been if it was a normal resistor, right? So just as a reminder, if I have a normal resistor and I want to know its drain current noise density, right, that would just be 4 kT times 1 over R, where, of course, 1 over R is just the conductance, right? So here I've given you the conductance of the diode. We again just said that that's ID divided by kT over Q. So again, if I wanted to model the sort of effective thermal noise that should have been coming from the diode, then I would basically say that it's just going to be 4 kT times the conductance of the diode. But notice this conductance is proportional to 1 over kT over Q, right? So in other words, when I plug this in, the kT is just going to go away. I'm going to end up with a drain current on the top, and the electron charge is also going to come to the top. In other words, I end up with something that basically says I should have gotten 4Q times ID. Okay? So this is now kind of interesting, right? Because we just said a second ago that with shot noise, what I should have gotten was 2QID. But I just did this sort of, granted it was kind of a hack, but I did this kind of simple experiment that now said, well, I should have gotten 4Q times ID. Well, this is kind of where this link between shot and thermal noise maybe is hopefully a little bit more apparent in that, well, it's off by a factor of 2. But if you kind of think about, let's say, random processes and random events and things like that, if I have a barrier that's forcing current to only flow in one way, it's kind of like saying I'm throwing away half of the random events that could have happened, right? Because anything that would have been associated with things flowing in the other direction basically isn't allowed by the barrier, right? So from a sort of variance standpoint, if half of my events don't matter anymore or don't really contribute any noise, then it's as if saying that my net variance should be half of what it would have been if I allowed both of those things to happen. Does this kind of make sense to people? Or? Now, by the way, you have to be a little bit careful with this, exact, let's say, analysis here. There's some people that have argued that this really is fundamentally what's going on. It's not, 100% clear that that's really true in all possible situations you can think of, but it is kind of a useful analogy to think about. But really, maybe the most important take-home message is that anytime you have essentially current flowing through a barrier, meaning that potentially it could only flow in one preferential direction, that will have shot noise associated with it. Does this make sense to people? Or? Okay, so other than diodes, what other sort of circuit element that you might be interested in do you think would actually have shot noise? Say that again? Okay, it turns out MOSFETs can have some shot noise in them, although most of the time when we use them, they typically don't. There's actually, again, some, let's say, fairly interesting, more detailed discussions there. But, what other kind of circuit element that, okay, maybe you guys haven't dealt with as much, but, in the good old days, quote unquote, was a very, very common circuit element to be using? Yeah, BJTs, right? Because in a BJT, of course, the whole thing is basically just a bunch of diodes, right? Okay, it's a slightly more sophisticated diode because there's, current being swept through space charge regions and stuff like that. But long story short, looks like a bunch of diodes, okay? So if we now want to sort of do the noise model for a BJT, then indeed we're just going to be basically relying on what we know about already for resistors and for essentially diodes. Now, there's a couple of really important points that I want to mention here. So the first is, what I'm drawing here is really the sort of small signal model that you would use for calculating noise. And by the way, in general, when you're calculating noise with active devices, you'll almost always do it with the small signal model rather than a large signal model. Because, well, maybe not by definition, but hopefully, if you're talking about noise, that should be a relatively small perturbation around a bias point. Right? If it's not, then probably something else is wrong. Okay? So the other sort of important thing I want to mention here is that anytime you have sort of a real physical device, you're always going to have just resistance making a connection to the device itself. Okay? And of course, anytime you have that resistance, it's also going to have noise associated with it. So in this small signal model here, I took sort of the standard, small signal model you've seen for BJT a bazillion times. And all I did was I just added some explicit resistors at the base, collector, and emitter terminals, and then added in the noise voltage sources, in this case, associated with each of those resistors. Okay? Now, the other thing I'll sort of mention is that you'll notice I basically put this IB squared here and this IC squared there. Those are really sort of the shot noise associated with the base to emitter junction and with essentially the collector to emitter current that's flowing. Okay? And so again, this is very much saying, well, these are basically diodes. So I'm just going to model those as being shot noise currents. And so you can see, for example, for the base current, I'm just saying that that noise current is 2Q times the base current times delta F. Don't worry so much about this for right now. We'll come back to that a little bit later on. Okay? Similarly, for the collector, I just said that it's 2Q times the collector current times delta F. Okay? So the last very important point that I'd like to make here that I want to make sure you guys get from the slide is that I added in these noise currents basically to model what was physically happening with the diodes. But notice I have no noise current whatsoever associated with this output impedance, right? And in general, you have to be very careful to never add noise currents due to small signal sort of output impedance elements, okay? Because what you have to remember is that noise is really kind of coming from the physics of the operation of the device, right? It's really related to essentially charges, how much charge is present in the channel, or charges jumping across barriers, and so on and so forth. Output conductance, that's really just sort of your way of modeling what happens locally in the sort of, if you change some voltage in that device, okay? But these small signal elements, they don't really generate noise because they're not actual physical resistors, right? They're just your model for a whole pile of other stuff that could be happening under the hood. Okay? So whenever you're talking about noise, you always have to sort of model the noise sources due to the real sort of fundamental physics of the device, and then add them into the small signal model, which could be basically abstracting a whole bunch of other things underneath it. Does this make sense to everybody? Or? Okay. So if that's the case, then obviously the sort of circuit element you're probably going to spend the most time thinking about its noise is a MOSFET. Now, with MOSFETs, unfortunately, things are a bit more complicated than what we've talked about so far, simply because MOSFETs have all these different operating regions, right? And so what I'm going to do now is we're going to start just talking a little bit about what does the noise current of a MOSFET look like in all of the different operating regions, okay? Now, the first operating region I want to spend some time on is actually just, in many cases, the simplest one, which is the so-called triode or linear region of operation, okay? Now, can anybody take a guess why I claim that this is actually the easiest region of operation to think about, from a noise standpoint specifically? Say that again? Yeah, it just looks like a resistor, right? So in particular, if we just sort of think about what's happening when I have a triode MOSFET, and again, I'm going to go back to drawing, some of these pictures of channel charge and things like that, but I promise it won't be too much, okay? So in the triode region, particularly if I'm deep in triode, meaning that I literally apply 0 VDS across the device, and of course I just apply some VGS to get it to be turned on, then if you think about the channel charge, right, it's basically completely flat, right? Meaning along the entire channel, I have kind of the same charge density. Well, if that's the case, the whole thing just looks basically like a linear resistor, right? There's just some resistance associated with that channel charge, okay? So that makes life really nice, because it basically just says, if we know what that resistance is, then we can also immediately say what the thermal noise associated with that resistor should be. And indeed, for at least a long channel device with sort of the simple quadratic model, we could just say that the conductance with that 0 drain to source voltage across the device is just mu Cox W over L VGS minus VT. But basically that's, even that equation is not super important. It's just telling you if you knew what the conductance at that 0 VDS is, you could then just model the noise directly as essentially being the noise current variance equal to 4 kT times that conductance, of course, times the bandwidth. Okay? So again, this GDS not parameter here, it's really just capturing what's effectively the resistance of the MOSFET in this triode region of operation. So now, why does life all of a sudden get a lot more fun when you're in saturation? Which, of course, for better or for worse, is going to be the region you're probably going to mostly care about, given that this is an analog class. Channel pinch-off. Okay, so you're right, but what do you mean by that? How does that sort of complicate this picture? Yeah, exactly. So the trick with saturation is that unfortunately now the charge is not going to be uniformly distributed. Okay, and actually let me just draw the picture here because I have a little bit more space. Okay? So now let's indeed say that we have a saturated device. Okay, so now instead what I'm basically going to get, and I'm just going to make the transistor a little bit bigger to make my drawing easier, is indeed some channel charge profile that looks like this. Okay? So obviously I still have to come up with some way of modeling the noise of this thing. So what do you think is kind of a reasonable approach to try and take? Okay, yeah, you said you're going to throw a gamma in there, and at the end of the day, that's absolutely correct. But how in the world did you come up with this so-called gamma? And by the way, I assume that your gamma you're referring to is you're just going to scale this number by some gamma. That's correct, but again, how in the world would you come up with that gamma? And by the way, somebody did actually come up with a reasonably precise gamma, so there is a way to do it. Okay, you said you're going to integrate across the channel. What exactly do you mean by that? That's correct, by the way, but what do you mean? Okay, you said integrate the charge density. So just to be really, really clear, what's the sort of one element we know very, very easily how to compute its noise from? What was the whole argument right here that we made? There's a resistor. Okay, so how about we just take this channel right here, and kind of like you were implying, we basically say, well, okay, this whole thing is some big nonlinear disgusting thing. But if I sort of zoomed in onto one small piece of that channel there, right, I could always model that as being some equivalent resistance, right? And then similarly, I could take the next small piece of channel, model that as another equivalent resistance, next small piece as another equivalent resistance, and so on and so forth, right? And indeed, if I do exactly this procedure, and then just integrate up the total contribution of noise from each of those small chunks of resistors, that's exactly how you could find out what the effective noise of the MOSFET would be in the saturation region. Okay? So it turns out that if you actually did exactly that experiment, and this was, I believe, first done by a guy named Van der Ziel. And if you're interested in the details, definitely go check out that paper. I think it's back from the, 1940s, 1950s, something like that. So if you go and you do exactly that sort of integration, you'll find that, nicely enough, you'll indeed get a drain current noise density that basically just becomes exactly the same as what it was before, meaning 4 kT times GDS naught times delta F, but scaled by this so-called gamma factor, which in this case, at least for a long channel device, turns out to be 2/3. Okay? So just to sort of deconvolve this expression here, this whole piece right there is just GDS naught. So really, this is exactly the same expression as we had before, just scaled by a factor of 2/3. Okay? So in particular, what we're basically doing is we're saying that because now the sort of channel charge is not flat anymore, it has usually this kind of triangular-ish shape. And by the way, because it's a triangle, you can kind of roughly guess why it would be a 2/3 factor there, just when you do the integration. What we're basically saying here is that, because it has that triangular shape, what we can essentially do is just substitute gamma GM for GDS naught. Okay? And in particular, this is sort of working out because it turns out that for a long channel device, GM is just equal to GDS naught. Okay? At least ignoring channel length modulation and things like that. And by the way, if you don't believe me, just look at the expression above. You'll see indeed that's exactly what GM would be. Okay? So if we just say, hey, well, we have essentially what in terms of the conductance, we have the same conductance as we had back in the triode region. Just that because it's sort of shaped by this weird channel distribution, there's that gamma factor in front. Then indeed, I can now just say that, okay, my overall drain current density is 4 kT gamma GM. Okay? Where again, that gamma GM is just replacing the GDS naught. So by the way, this is the expression we'll be using probably the most throughout, kind of the entire rest of the semester. So it's kind of worth remembering. But there are a few caveats that we do have to be a little bit careful of here. So the first one is that, the sort of procedure that I explained to you here is basically the correct procedure. But you really have to be pretty careful about getting that channel charge really exactly right. Okay? So if you actually look at sort of, how, for example, SPICE will really calculate this, or how a more accurate model will do it, it'll really go and calculate the exact details of the charge inside of the channel, and then based upon that charge, figure out sort of the noise contribution from each incremental piece of the channel and integrate it all up. Okay? But of course, that's a bit complicated, and in terms of, like, say, doing any hand calculations is really, really difficult. Okay? So the only other thing that I should mention is that even though exactly that expression is sort of what we really are going to use, it turns out there's some issues that we have to be, again, very careful about. Okay? So in a sort of short channel device, it turns out that unfortunately GM is not exactly equal to GDS naught. Okay? And so because of that, there's kind of a new factor that you typically have to introduce, which is what's the relationship between GM and essentially GDS naught. Okay? Because again, remember the whole sort of derivation we did was by relating GM to GDS naught and then knowing how much thermal noise GDS naught would actually have in the first place. So because those two are not exactly the same, people introduced a new parameter that basically said that GDS naught was equal to something like GM over, not gamma there, alpha. Okay? So that alpha factor is kind of like another proportionality constant between what GM and GDS naught really are, at least from the standpoint of a sort of thermal noise behavior. Okay? Now, the bad news is that this alpha factor is, let's say, not very well defined from a physical standpoint. Like, it's really hard to say exactly what that alpha factor should actually be. And so you can see some pretty wide variations in what that number turns out to be, even in the same device, just in different operating regions. But typically speaking, if you sort of looked at 1 over alpha, that number is about 2 to 3. In other words, the sort of drain noise current density you would get is roughly 2 to 3x higher than you would have expected it to be based on the purely short channel derivation. Okay? So again, as I mentioned before, I will actually mostly use this expression here. So I'm just going to be basically kind of lazy and say that it's 4 kT gamma GM. But you should remember that gamma may not necessarily be 2/3. Okay? In particular, gamma is probably more like 4/3 or 2 or something like that. Okay? In other words, you should remember that the real expression is actually this. It's just that because because gamma over alpha is really at the end of the day just one parameter, I'm not going to keep writing gamma over alpha repeatedly. I'm just going to basically call it gamma. Does this make sense to everybody? Or? Okay, so we've spent a lot of time talking about the drain current noise of the MOSFET, but it turns out there's a couple of other sort of sources of noise that you can pick up as well. In particular, it turns out that the MOSFET actually has sort of intrinsic noise due to the gate itself. Now, this is a little bit weird, because if you remember, we said that a MOSFET kind of just has a capacitor for its input impedance, right? And we said capacitors can't really generate any noise. Well, turns out we're sort of lying ever so slightly, because what really happens is that, even the instant that you put a sort of new voltage signal on the gate, it takes some time for basically the electrons or holes or whatever it is inside of the MOSFET to actually show up in the channel. Okay? So because of that time delay, there's effectively kind of like a resistance in series with that gate there. That resistance, of course, generates thermal noise. Okay? Now, the good news is that this is largely only important at pretty high frequencies. So for most of what we're going to do in this class, that probably doesn't matter too much. But in particular, if you take like 142, 242, you may spend a lot of time talking about this so-called gate-induced thermal noise, because it could actually have a pretty big impact on the performance of your circuits. Now, it turns out there's another thing we have to be a little bit careful about, particularly in modern technologies, which is that if you guys remember, we spent a lot of time sort of mentioning how, unfortunately, the oxides are thin enough you can actually tunnel directly through the oxide. Well, if you think about it, if I've got current flowing through there, in other words, I've got an electron jumping over a barrier and ending up on the other side, that's exactly the situation we set up for shot noise, right? So indeed, you can actually get a reasonable amount of shot noise due to this gate leakage current. And by the way, just in case you're sort of thinking, well, maybe I'm just mentioning this and it doesn't matter at all, user beware, because particularly in some of the, let's say, not latest and greatest technologies, but maybe a generation or two back, 90 nanometers was actually about the worst for this. It turned out that if you looked at sort of a transistor, a MOS transistor, at the maximum supply voltage, and you sort of, again, closed your eyes, treated it as a black box, and you said, well, I'm just going to sort of look at this thing and look at, gate current and drain current and things like that. The so-called equivalent beta you would get, meaning the ratio of the drain current to the gate current, was only about 3,000 or so. Okay, so in other words, it was kind of a pretty good bipolar, but not like was within the realm of definitely bipolars and not MOSFETs in terms of gate current to actual drain current. Okay, so again, just be careful of that, because if you do have substantial gate leakage, it could also show up as a reasonable amount of noise at the input. You better add that, of course, to your model. Make sense to everybody? Or? Okay. So with that, hopefully the sort of next step should be fairly obvious. So we talked about triode, we talked about strong inversion. The only sort of thing we have left to mention a little bit is just what is the noise current of the MOSFET in the weak inversion. So in that case, what do you guys think is the sort of right model for the noise current once the MOSFET's in weak inversion? Yeah, it's exactly like a BJT. It should be shot noise, right? So in other words, just as a reminder, once we're in weak inversion, our equivalent model really for the transistor, for the MOS transistor, just basically becomes effectively a BJT. Right, we have the oxide capacitance, depletion capacitance. This is, of course, our gate. Then we have our let's say, drain and source, drain, source, gate, right, where, of course, the base potential is being controlled by that capacitive divider. Okay? So indeed, given that we really start looking like a BJT once we enter that weak inversion region, then now our drain current density will just be equal to 2Q times the drain current. Okay? Simple enough, makes sense. Once you start behaving like a BJT, the thermal noise should also behave like a BJT. Of course, we have to be careful. There's, it's not exactly a BJT. There is a sort of degradation factor in the front here. But in terms of the thermal noise, that is indeed correct. Okay? Now, of course, the somewhat bad news is that many of the effects that we've mentioned may or may not be directly captured by your SPICE model. Okay? So if we draw the sort of small signal noise model that you would typically see, as I mentioned before, you typically won't have the sort of gate leakage or the gate noise intrinsically built into the model, just because it didn't really used to exist, and so it's not part of the sort of standard model decks that people come up with. So again, watch out for that. And secondly, depending upon sort of which version of the SPICE model you're using, remember BSIM is kind of like one of the industry standard models that's out there. BSIM 3, I should say, is about 5 to 10 years old now. So actually, most people use what's called BSIM 4. But long story short, just be careful because your model may or may not include all of the short channel effects completely accurately. Okay? And so if it doesn't, you need to make sure that you do a simulation, you look at the drain current noise density from the MOSFET, and it actually looks reasonable, right? You just do the hand calculation, see, well, okay, is it giving me a gamma of like a third? Is it 2/3? Is it 3? Like just to kind of make sure that it's in a reasonable range, not something that physically is not even possible. Okay? Does this make sense to everybody? Or? Okay, so the last thing I want to mention for this particular sort of, let's say, introduction to the different types of noise that we'll be interested in is that it turns out there's even yet one more type of noise that can actually play a pretty substantial role, especially if you're doing some very high precision and lower frequency types of circuits. Okay? So this noise is what's called flicker noise, or 1/f noise, or because from whatever reason people like to use color analogies with noise, this is also sometimes referred to as pink noise. Okay? Don't ask me where pink came from. That's just what they came up for it. So out of all the sort of noise processes that we've talked about so far, this one is kind of the most quote-unquote mysterious. Okay? And the reason for that is that it is very strongly dependent upon essentially manufacturing-related defects. So in particular for the MOSFET, the kind of dominant theory for where flicker noise comes from is basically the following. So if we look again at our sort of transistor, right, we've got sort of the piece of poly, we've got some gate oxide, right, and then we have our sort of source and drain and the channel underneath it. Okay? Well, turns out that no oxide you build is ever exactly perfect. Usually there's some kind of quote-unquote defect inside of it that people usually refer to as a trap. Okay? And anytime you've sort of got one of these traps, it turns out that every once in a while, an electron, or a hole for that matter, but typically electrons, can basically jump out of the poly gate and into that little trap and get stuck there. Okay? And by the way, it's called a trap exactly because it traps charge, meaning electrons or holes or whatever get stuck in that particular region. So if you all of a sudden have an electron that jumps into the oxide and gets stuck there, how does that sort of affect the transistor from the sort of parameters that we typically think about? What does that do to it? Okay. So there was two different things that were said. One was that it increases Cox, and the other was that it affects the threshold. Say that again? Oh, decreases. Well, so it turns out that it doesn't actually modify the sort of oxide capacitance really very much, because it's really just sort of one electron, so it can't really screen much charge on the other side in terms of really acting like sort of a capacitor plate. But indeed, what it actually does is basically changes the threshold voltage. Okay? Because all it does is it says, well, there's now I need one less electron on the other side to essentially have the same equivalent voltage applied, okay? Or one less hole for that matter, okay? So if you change the threshold voltage of a MOSFET, of course you change the drain current density for a fixed gate-to-source bias, right? That therefore means that indeed this sort of process of electrons hopping into these traps and out of the traps can actually modify the or can cause not thermal noise, can cause noise at the output of the device in terms of a drain current. Okay? Now, what's really interesting about this particular one is that unlike all of the things we've talked about so far, it actually has a frequency-dependent noise density. In other words, if you do a plot of the drain current noise density versus frequency, what you'd actually see is that it increases as you go to lower frequency. Okay? By the way, anybody sort of, just from the discussion we've had so far, have an idea of why it is that that happens? Why is it that, essentially this is saying if you wait longer, the variance you expect to see is larger?
Well, kind of like if you're running a low frequency, your electrons are going to get stuck and that gets washed through as much. So maybe you would see like more variance from time to time.
Yeah, so you kind of were going in the right direction. You said something like, if I wait, if I'm at lower frequency, that kind of implies that I'm waiting a longer period of time, meaning I'm sort of averaging all of these effects over a longer period of time, right? Well, if you sort of think about this physical process here, if the electron jumps in there and basically gets stuck, then what I'm doing is if I wait longer and longer, I have more probability of picking up more electrons that get stuck, right? And obviously, statistically speaking, the more sort of electrons could possibly get stuck, the larger the net variance of the final noise will be. Now, this is not to say that electrons can't actually jump back out or holes can jump in or whatever. They actually could. But the point is just that, the longer you wait, the more of these independent events you actually add up. And so the larger the final variance of the noise you see will actually be. Okay? So if we just take an example, by the way, I should mention, as I said, this is really strongly process dependent because you can imagine the actual sort of, the real variations you see are highly dependent upon how many traps there actually are in the oxide, how quickly or how easily it is for electrons or holes to jump in and out of those traps, and so on and so forth. So, it's hard to make necessarily universal statements about exactly what those numbers are. I'll come back to you in one second. But typically, or at least for our particular process, the kind of 1 over f noise, let's say, coefficients that you would expect to see are quoted up over here on the top. And basically, the overall 1 over f noise current density, or current that you should get from a particular transistor, is kind of given in this expression here. So that kf just shows up as the process-dependent parameter. Notice it's proportional to the drain current, but it's inversely proportional to Cox and to the channel length squared. So just before I sort of ask you guys a couple questions on that, there was a question.
Yeah, so I'm wondering if you're kind of getting these like electrons jumping in, is reversing the polarity, so like having your AC thing actually going to like scoop them out somehow?
Okay, so this is a great question. So the question was, if this is really all about electrons kind of jumping in and getting stuck, if you reverse the polarity of the voltage that you apply, will that actually help reduce this noise? In other words, would it make it so that things that got stuck could actually get swept back out? This is actually somewhat of an open topic for debate. In principle, yes, and indeed there's actually been some measurements that have shown that if you actually play that trick, it really does help with this 1 over f noise. But the results have not been completely conclusive in that in different process technologies, people have seen that it either really did work very well or not. And like I said, I think that's strongly related to exactly what the physical defect mechanisms are and whether or not you really are effectively able to sweep those electrons out of the traps. Yes?
Are those gas just for strong inversion, or is this?
Okay.
Like this is kind of a bias point dependent.
Yeah, these KFs most likely will be somewhat bias point dependent. So here I'm just sort of giving you the rough number for a given bias point. So obviously you should be very careful to sort of look into the details of the model. Particularly if you've got sort of a good model, then it should be capturing the bias point dependent KF there. But to zero order, you can kind of take these numbers as a reasonable guess to start from, at least for our particular technology. Again, user beware, these numbers could vary quite a bit from one technology to the next. And I'll kind of give you some let's say, representative ways of back of the envelope figuring out what those numbers will be in 1 second. Before we do that, though, I did want to ask you guys a couple of questions. So first is that notice this noise current density from the 1 over F is proportional to 1 over the oxide capacitance. And just as a reminder, that Cox there is just epsilon ox over Tox. So why is it that increasing that oxide capacitance decreases the effect of this flicker noise, at least from a drain current noise standpoint? What's happening there? Okay, so you said that if you decrease the thickness of the oxide, then maybe you have actually less physical traps. That might be possible, although that would probably be captured more by that kind of KF parameter. This is actually really just directly related to how the charge causes a noise in the first place. In other words, even for the same sort of defect densities and everything else, I claim that if you reduce the thickness, things will get better.
So the higher capacitance, you have a lower change in VTH for a trapped charge.
Yeah, exactly, right? So the whole trick there is that if your oxide is thinner, the gate oxide capacitance is larger, meaning that for the same voltage applied to it, right, moving one electron in and out, relatively speaking, has less of an effect, right? Because you had more charge to begin with. So the other way you said it was that that one charge has less of an effect on the threshold voltage. Okay, that's indeed exactly what it is. The thinner the oxide is, the less one charge could actually modulate the threshold, and therefore the smaller, let's say, an absolute current density variation you should actually get. Okay? Okay, well, so here's the second question for you guys. Why is it also proportional to 1 over the length squared? How does that happen? And by the way, I'll give you a hint. This is sort of similar to the discussion about why the drain current density in a long channel device was somehow proportional to VGS minus VT squared, and that there's two independent mechanisms that both are sort of proportional to the length, or 1 over the length. So how might having a longer device help you to reduce this noise? Okay, so you said that the threshold gets more constant. I guess what you mean is it's more constant versus the channel length. So unfortunately, that's not quite the exact effect here, although there's a related effect. By the way, what happens to the capacitance of the device as you increase the channel length? Yeah, capacitance goes up. So if I've got one electron jumping in and out of a larger capacitor, how much voltage change gets induced due to that effect? Or rather, does it get larger voltage change or smaller voltage change if you increase the capacitance? Yeah, it's a smaller voltage change, right? So much like we said with Cox, if you make the transistor just physically longer, then effectively you're kind of increasing the total capacitance at that gate. And so for each electron that's jumping in and out, basically you're reducing its net effect on effectively the threshold voltage, okay, or equivalently the noise current density. By the way, another way of saying this is that just generally with statistical things, right, if you average over a larger area or a larger number of events, the sort of mean to variation ratio gets better. Okay, so that's one reason why increasing the channel length helps. What's the other reason that increasing that channel length actually reduces the drain current noise density? Are you increasing the total drain current? So by the way, notice I've fixed the drain current here. Right? I'm externally biasing the device. So for a fixed external drain current, if I increase the channel length, what's going to happen to the sort of device? Lower the resistance? Well, and by the way, I'm talking about the MOSFET channel length. I'm not talking about a normal resistor here. Give you guys a hint. What was the sort of, long channel MOSFET drain current versus dimensions and voltages and et cetera equation? What terms were in there? And I'll maybe even go back to this slide right there. So what pops up in that? This is the GDS, of course, but what pops up there? Okay, there's a gamma, yes, but, we were asking about channel length before. Right, notice there's a 1 over, oh, that's interesting. There's a 1 over L in this expression here. So if I keep the drain current fixed, and I basically increase the L, what's going to happen to the sort of size of the device? In other words, what's going to have to happen to the width of the device? Go ahead. Well, okay, it's going to go up. That's right. So if I double the length, then to zero order for the same current, I have to double the width, right? Well, if I've now done that, then remember we said that making things larger in space, meaning averaging over more events, makes it better. Well, exact same thing here, right? Or really just to say it another way, if you increase the channel length, then for the same drain current, your GM gets smaller. Right? So for the same voltage that you changed at the gate by moving that electron on there, once again, you have less drain current effect at the output. Okay? Does this make sense to everybody? Okay. So here I'm just kind of giving you some example numbers for what that drain current density actually is. Okay? So you can see that, for something similar to our technology where Cox is about 15 femtofarads per micron squared, then roughly speaking, if we sort of look at the total integrated noise, you're going to get something like on the order of a nanoamp to maybe 1.5 nanoamps. Now, there's one sort of thing that should hopefully or probably bothered you a little bit by this point, and it bothers most people when they first look at flicker noise. And they usually say, well, wait a minute. This noise current density here, if I really have a 1 over F behavior, it seems like something really bad is going to happen if I go to lower frequencies, right? So in particular, if I go to 0 frequency, what does this sort of equation predict? Yeah, it predicts infinite noise. So usually this bothers people. Now, I claim that this actually should not bother you too much, but why do I say that? Why am I kind of okay with you having infinite noise at DC? The bandwidth is also small. Okay, you're actually going in very much kind of the right direction. You said the bandwidth is also small, but I'm really literally going to wait forever. Okay, I'm literally going to wait until I hit absolute DC. Why do I not care if the noise is potentially infinite? Even though you're absolutely correct, the bandwidth is small, but nonetheless, I could actually get an infinite amount of noise out of it. Why do I not care? There's a very practical answer here, by the way. Okay, well, you said I don't build circuits with 1-year time constants. 1 year I might actually build, but do I care if my iPhone works infinite number of years from now? Oh, I don't know about you guys. I don't, because I'm going to be long gone, right? And pretty much everything else that I could ever have thought of is also going to be long gone, right? So in other words, the fact that it goes to infinity if you waited forever, well, okay, fine, I waited forever. Everything, physics says that everything should have exploded by then anyway, so who cares? Right? Now, the other sort of trick here is indeed that maybe I'm not building circuits that have time constants of 1 year, but I do actually want my circuits probably to operate for, well, okay, maybe not for a year continuously, but for days or a month or something like that, right? Or maybe even if I'm doing some really weird thing, I actually do want it to operate continuously for 1 whole year, okay? So in that particular case, I would actually want to make sure that even the noise I integrated over that full 1 year of operation was sufficiently small. Now, this is where the argument about bandwidth actually comes in. Because remember, this is indeed a noise current density, right? So if I actually want to know how much total noise I have due to that effect, I have to do this integration that we had mentioned earlier, right? And hopefully, like you guys kind of remember from high school calculus or whatever it was, if you do an integration of something that has a 1 over x dx, at the end of the day, you get a natural log of basically the frequency ratios, okay? So that's really good news because it basically says that, hey, look, if I'm taking something that operates at like, I don't know, even a megahertz, right? And yeah, maybe I take it from, let's say, from 1 second even all the way down to 1 year. The kind of number of orders of magnitude between 1 year and 1 second, in terms of the net, frequency bandwidth, is really, really small compared to the 6 orders of magnitude I have between 1 hertz and 1 megahertz, right? In other words, I've just got a lot more bandwidth at the higher frequency parts than I do at the lower frequency part where that density really starts exploding, okay? Maybe just from a purely, let's say, mathematical standpoint, because I have this logarithmic behavior, you can really reduce this low frequency limit over which you're trying to operate the circuit over quite a bit and still not have a huge impact on the net variance of the noise that you'll see. Okay? Does this make sense to everybody? Or again, this is a fairly popular point of confusion, so if you have questions, please do speak up now.
Were you saying that you want something to operate for a year? Are you saying that you want your time constant to be, or is it something you'd be operating for?
Well, so you said if I want the thing to be operating for a year, you were asking if I mean that the time constant is a year, or do I mean really that it's operating for a year? So what I actually mean is that it's literally operating for a year. Because let's just say, for example, you have a circuit that's DC coupled at its input, right? Let's say I had an amplifier or something, right? If it's just sitting there and running for 1 full year, then I'm going to integrate out to 1 full year in terms of the quote-unquote bandwidth that I'm interested in. Now, it is going to say that, of course, the sort of total variance of noise you'd see from time 0 all the way to time 1 year would go up, right? But really, the meta point here is that it's not going to go up by much. So in other words, even if you said you wanted to operate at 1 second versus 1 year, it would only cause you to increase the sort of noise you'd budget for by a relatively small factor. Okay? And by the way, this is exactly a problem you're going to be doing in your homework. You'll see what the real implication of it is. And you'll see it's, it may have to cause you like a factor of 2, but it's like going from 1 year or 1 second to like a year, a month, 10 years, something like that. Okay. So the other thing I'll just briefly mention in terms of flicker noise here is that typically speaking, rather than sort of directly dealing with what that flicker noise current density is, people usually like to think of the so-called corner frequency. And so what they mean by that is just the following. So we said that in a MOSFET, we certainly have the thermal noise just due to the drain current itself. And if we do a plot of kind of that noise current density versus frequency, then we said that that's basically white. In other words, you see something kind of flat like this, right? Well, it turns out you also have to add in this flicker noise. And we said that a second ago, that has this 1 over f kind of profile. So if I looked at kind of the total noise coming out of the device, well, when you add those two things together, and again, of course, you have to do this in variance, you'll see something that kind of looks like this blue curve that I'm drawing here, right? So below some frequency, it'll kind of be dominated by the flicker noise. And above it, it'll just be dominated by the thermal noise. So the kind of figure of merit that most people like to quote is this so-called corner frequency. Okay? And that corner frequency just tells you if you go below that frequency, you're now dominated by flicker noise instead of by the thermal noise of the device. And obviously, the sort of higher that corner frequency is, the more dominated you are by flicker noise. Okay? And you can, of course, also think about where that corner frequency is kind of relative to the frequencies of operation that you're interested in. That'll also give you an idea of sort of how much of an effect flicker noise would really have. Okay? So I kind of did a simple derivation of how you can approximate what that corner frequency really is. That's not really sort of super critical. What's more interesting is just to have a little bit of an idea of what the typical numbers end up being. So again, back in the quote-unquote good old days, typical numbers that you would see would be somewhere on the order of hundreds of kilohertz to maybe a few megahertz. Okay, so I actually took some of the numbers that we had, and I took actually a V-star of 100 millivolts, so in other words, a device pretty close to subthreshold. In our technology, you can see this came out with something like a couple megahertz or so for the NMOS. Of course, if you increase the channel length, it goes down very, very quickly. But you should actually have in mind that, especially for some of these more modern technologies, let's say 45, 65 nanometer, maybe even 22 or whatever it is, you can actually even start seeing corner frequencies out in the range of a gigahertz or so. Okay? And that's really just happening because the devices that you have are really, really small. Okay? And so if you have a really small device, again, you can get some pretty large corner frequencies in terms of, or really pretty large effects due to that 1/f noise. So the good news is that, at least in our technology and for most of the things we're going to be working with, basically the bandwidths that we're interested in are going to be pretty large compared to the corner frequencies. And so because of that, we can largely speaking sort of ignore the 1/f noise. But again, user beware, because that's not necessarily true in all applications, right? So especially if you're doing some, very high precision kind of things, flicker noise can have a very, very big role in the net, basically noise performance that you can get out of your circuits. And by the way, we'll talk some more, probably in 5-6 more weeks or so, about some techniques we can use to actually combat flicker noise explicitly. In other words, really try and get rid of it using circuit level techniques rather than just by sort of sizing things up to be larger. Any kind of questions on this? Or? Okay. So if not, this last slide here is just kind of a reminder of how we go about actually doing these noise calculations. But rather than actually going through it here, I'd like to move to the next set of lecture notes. So this is the slide, lecture notes number 6, because we'll be sort of reviewing that and actually using it in more practical contexts here. Okay, so the basic way that we sort of discussed to actually do these calculations with noise in the previous lecture, even though we maybe didn't explicitly sort of point it out this way, is actually pretty simple. Okay, so let's just say that you had, you had some amplifier, and in this case, I'll just draw some very simple, common source NMOS amplifier with an ideal current source load. Okay, what you'd basically say is, well, okay, I'm going to take this amplifier. And the first step is that I'm just going to write the small signal model for it. Okay? So in this case, it would just be a GM times the input voltage, and of course that load capacitance at the output. Okay? The next thing is that since I'm actually interested in noise and not in the signal itself, not the signal behavior, then I'm basically just going to say, well, hey, the input is actually 0. And so in this particular case, that's going to knock out the GM completely. Okay? Then in this case, I know that I want the output voltage reference to ground for this particular circuit. And so now we're just really going to follow the procedure that we had mentioned before, which is that for each possible noise source in the circuit, in this particular case, the only one is going to be due to the drain current noise of the MOSFET. I'm basically going to calculate what the transfer function from that source to the output is. And then once I have that, I can essentially integrate it and just add each of those sources together, right? So that's, again, really all that this thing here is saying. I just take each possible noise source. So that's why I'm iterating over this x. I figure out what its transfer function is. I multiply the sort of transfer function by the noise, either current or voltage density. And then at the end, if you want the total noise, you just look at this integrated value. Okay? So conceptually, actually, this is really, really simple. But you can imagine this can get a little bit tedious. Okay? So what I want to do now is kind of show you a couple of specific examples. But before I do that, I do want to sort of tell you or give you maybe a little bit of a cheat sheet. Because it turns out probably the number one thing you sort of spend time on in doing these noise calculations is just figuring out what the heck those integrals actually are in the first place. Okay? So because of that, that's why I've given you this cheat sheet that just tells you the answer from the get-go. Okay? So as an example, if you had a very simple first-order low-pass filter, then it turns out the sort of integral of this first-order low-pass filter is just omega naught over 4, where omega naught is kind of the bandwidth of the filter. Okay? Now, by the way, the sort of way you should interpret all of these integrals is, you remember I kept using that delta f in all of the expressions before? these integrals are really what actually tell you the effective bandwidth. Okay? Because unless you know what the sort of exact transfer function is, you generally speaking aren't working with like brick wall kinds of things, right? It's not that you're interested in exactly bandwidths from X hertz to Y hertz, right? You actually have some transfer function, some real filters that you've built, and that would actually tell you what the real bandwidth is. So again, the way you sort of interpret all of these integrals is that once you know the transfer function, that's really is what's setting the effective bandwidth that you use inside of that delta F term over there. Okay? And one thing that to notice that's kind of interesting here is that in this particular case, this is actually saying that the sort of effective delta F is basically equal to the cutoff frequency of the filter times essentially pi over 2. Okay? And the way I got to that was, of course, just that omega naught is 2 pi times f naught. Okay? So notice, interestingly enough, the sort of effective bandwidth is actually wider than the low-pass filter sort of cutoff frequency, or the 3 dB point of the low-pass filter. So why is that? Why is it that we're actually seem to be getting more bandwidth than what would sort of be implied from the naive calculation we may have first done? What do you guys think? So by the way, I'll remind you, or maybe I'll ask you guys, what is the sort of shape of a first-order low-pass filter to begin with in the frequency domain? Yeah, okay, so everybody sort of made the right hand motions, right? So if we plot h of f, and I'll do it in the log domain just because I'm lazy to actually draw it the right way, versus f, you see something that kind of looks like this, right? Where, as I'm sure you guys all remember, this roll-off here is 20 dB per decade. Okay? So procedurally, when I'm doing this integral, what is it that I'm kind of doing? How would you sort of draw that on this curve here? Yeah, I'm taking the whole area under the curve. Okay? So what would this curve have to look like? And let's draw it again over here, maybe even in a different color. What would the shape of that filter need to look like in order for you to get exactly the cutoff frequency as your effective bandwidth? Yeah, exactly. It would have to look like this box, right? You'd have to pass exactly what's underneath and pass absolutely nothing from everything above it, right? So now you guys tell me, why is it that the low-pass filter bandwidth, or effective bandwidth, is actually larger than that cutoff frequency? Yeah, exactly. There's still actually a lot of noise that you're integrating after that cutoff frequency. And in particular, for a first-order low-pass filter, the kind of roll-off there is lazy, right? Meaning it's not rolling off very quickly, so there's still a reasonable amount of energy you pick up from integrating out in that frequency region. Okay? Okay, so you'll notice here that I actually I provided you the first order sort of integration, and I've actually also provided you the second order integration, and nothing really beyond that. So that's not to say that you're only going to be dealing with second order circuits in this class. Sorry, life's not quite that simple. But the good news is that once I've given you the integrals for first and order second systems, everything else can be basically derived from that, essentially by doing partial fraction expansions, right? You can always take any sort of polynomial and decompose it into quadratics times linear or so on and so forth. Okay? It's a little bit of a pain in the butt. I'm the first to admit that, but I've given you sort of the bare minimum you need to actually be able to do something productive. Okay? Another just sort of quick shortcut that I want to point out is that for this generic second order systems, and notice here, in these particular cases, I'm giving you either only sort of something with no zeros or a zero kind of exactly at 0. They both turn out to integrate to this omega naught q over 4 in terms of the net bandwidth. The kind of shortcut in terms of, once you've figured out a transfer function, you want to know that integration, Turns out that this is essentially just exactly the term in the denominator there, right? That's scaled by the s. If you just take the inverse of that and divide it by 4, that always gives you this integral here. Okay? So that's kind of the shortcut for if you see this kind of transfer function to immediately get to the integral. Okay? The only other thing I'll mention is that if you look at this form here, this is kind of a slightly more generic second-order transfer function, where I now have a 0 as well. Turns out you can actually derive this from these two expressions here. Because notice it turns out that something with no 0 and something with a 0 at 0, they both evaluate to the same expression here. So if you wanted to figure out what this was, you can just basically take this and add it to a scaled version of that, and you'll end up with exactly this expression that I have down here. So see, the 1 just comes from sort of this part of the integral there, and this scale factor, or this omega naught squared over omega z squared, is exactly just coming about from basically rescaling this s over omega z to look like s over omega naught. Okay? Only take-home point being that I'm very likely to forget exactly this expression, and every time I do, I just go back to this and rederive it. So I encourage you guys to basically do the same thing. Okay? Does this make sense to everybody? Or? All right. So in that case, let's actually do some real examples here. Okay? And the first real example that I'm going to go through is actually a pretty simple but very useful circuit. And it turns out that the final result you get is going to be very indicative of kind of all of the future results we're going to be seeing pretty much for the entire rest of the class. Okay? So the particular circuit I'm interested in is the so-called sample and hold, where the very basic idea is that I'm going to take some input voltage, and what I want to do is I just want to sample it onto a capacitor. Okay? So as an example, I may have an input voltage that maybe is a sinusoid or something like this. And then right when I turn off that switch, I just want that voltage to be held on the capacitor. Okay? Now the trick is, of course, that any switch that I may have, or in fact any voltage source that I may have, is always going to have some resistance associated with it. And well, once you have that resistance, that resistor is, of course, going to add some noise onto the actual voltage that you measure. And so, of course, when you turn off that switch, you're going to also sample that noise, right? You could get a slightly wrong sample out of the circuit. Okay? So let's just go and sort of quickly calculate what the noise on the capacitor should actually be due to the thermal due to the thermal noise of the source or switch resistance. Okay? Okay. So in the question was, are we assuming that the switch is ideal? We're basically using a model essentially like what I've drawn here, where if the switch is non-ideal, the only non-ideality is that it has some series resistance associated with it. Okay? Okay, so if we sort of exactly calculate this thing, then if we follow our standard procedure, right, then while the circuit is basically on, we're just going to have a very similar situation to what we drew before, which was we're going to have some noise voltage from the resistor, some resistance, and some capacitance, and of course at the end of the day, we're going to measure the output voltage over there. Okay? Well, okay, so we already know that the noise voltage density is just 4 kT times R, right? That's pretty easy. Well, and we also already know that the transfer function of this thing is, in terms of voltage to voltage, is 1 over 1 plus SRC. Okay? So again, just sort of following exactly our procedure, if you go and you look at the integral of this first order low pass filter, remember we said it was omega naught over 4? Well, in this case, omega naught is just 1 over RC. So the net integration of this is going to turn out to be 1 over 4 RC. Okay? Well, here's where the sort of magic happens. You take these two things together, you see that the noise is actually kT over C. Okay? Absolutely, totally independent of the resistance. Now, this, again, sometimes sort of bugs people, because it was the resistor that was generating the noise in the first place, right? But we just said that the total noise that we're going to get at the output absolutely depends on, has no dependence whatsoever on the resistor at all. So why is that? What's going on there? Yeah? Yeah, exactly it. Okay, so the trick here is that if you have a larger resistance, then indeed the thermal noise density you have from that resistor is larger. but you also start filtering it earlier. In other words, the bandwidth is lower. So indeed, if you sort of look at this, SPICE simulation, which by the way, you don't even have to do this in SPICE. You can do this kind of by hand in 2 seconds. But basically, if you look at this SPICE simulation, this is the example with a larger resistor, but a lower bandwidth, versus the example with a smaller resistor, but a higher bandwidth. If you look at the net area under those 2 curves, which is actually just what this red and kind of purplish or pinkish purple line are showing, and by the way, this is just showing you sort of the integrated noise versus frequency, you'll see that if you go out to you integrate from 0 out to infinity, indeed, the net noise that you get will be exactly identical. Okay? So this argument about, the noise density changing kind of the same way that the bandwidth does is one very good way of seeing this. I claim actually, though, that there's another very good way of sort of arguing why it has to be the case that the resistance doesn't actually matter at all. So in order to do that, I'm going to do this sort of energy-based analysis that says, indeed, doesn't matter what the resistance is. You should always get this result that says the thermal noise variance is kT over C in voltage. Okay? So in order to see that, let me just sort of make the following simple arguments. And I'll ask you guys some questions along the way. Well, if I just took a capacitor, right, and I asked you how much energy was stored in that capacitor, you'd hopefully immediately tell me, well, it was just 1/2 CV squared, right? How much energy did we say was available due to thermal noise in a resistor, or just more generally due to thermal noise? Remember, 4 kTr was in voltage. So how much energy did we say was available? How did we even get 4 kTr in the first place? Yeah, it's just kT, right? Okay, well, what do you think I'm going to do next? Yeah, I'm just going to say, well, the noise that's the energy that's available from the noise should be equal to whatever energy I'm storing on the capacitor, because there's nothing else I can do, right? Okay, well, so if I do that, hopefully it should be very obvious that I'm going to get that 1/2 CV squared is equal to kT. In other words, V squared is going to be equal to 2 kT over C. Okay, so now something's still a little bit wrong, right? Because notice I have an extra factor of 2 here. So hopefully you guys talked about this in 141. What's missing? Exactly. So the issue here is just like the issue you may have seen in 141, which is that if you took a voltage source that basically had a step, and you asked the question of how much energy got pulled out of that voltage source to charge that capacitor there, right? The simplest way to figure that out would be to say that, well, okay, the charge on the capacitor is just whatever the voltage is times the value of the capacitor, right? And the energy that came out of the source is just equal to the charge times the voltage. Well, and of course, if you do that, you'll indeed get that now you have CV squared in terms of the energy, okay, that came out of the source. So if you really sort of track things that way, meaning you say it's not just the energy that's stored in the cap that matters, it's actually the energy that came out of the source, you would then indeed say that you just have CV squared is equal to KT. And so you'd get V squared is equal to KT over C, just like we expected. Okay? Does this make sense to everybody? Or? Now, maybe just as a couple of side notes and then sort of one brain teaser to have you guys go home and answer for next time. The first side note is that it turns out, again, if you're kind of a statistical mechanics or physics kind of guy, you can get this exact same result from what's called the equipartition theorem. Just briefly, it says that for any sort of physical system, you get 1/2 kT of thermal energy for every degree of freedom. And so if I say I have 1/2 kT of free energy and I have 1/2 CV squared stored in the capacitor, again, you can come up with V squared being KT over C. So, again, another sort of very fundamental physical kind of intuition there. Now, it turns out that if you figure this out, there's a lot of really fun and interesting problems that you can also immediately solve. Okay? So I'm going to actually give that to you guys as a little bit of a homework. Okay? So the homework is the following. I'm going to have some noisy current source over here, just for example, coming from a resistor. Okay? And then what I'm going to do is, I'm going to kind of build the equivalent of a sample and hold. We're going to do it with an inductor. Okay? So in other words, the way this thing is going to work is, for some long period of time, I'm going to have this switch here on, so that I just have the noise current basically kind of flowing through this RL circuit. And then all of a sudden, I'm going to turn this switch off and turn this switch on, so that whatever current was stored in the inductor is just going to flow in this sort of closed circuit here, and ideally speaking, stay there forever. Okay? So the question for you guys is, what will be the variance of noise current sampled in that inductor? Okay? And I don't want you to do any integrals or anything like that. I claim you can solve this, question immediately from kind of first principles like we just discussed. Does this make sense to everybody? Or? So again, this is going to be like your mini homework. I'm going to randomly pick someone from the audience and ask them to answer this next time. And if you think that's a good time to not show up, I'll send you an email or something and count it against your final grade. Okay? All right. So unless there's any questions, we'll pick back up with that next time. So see you guys then.